Thank you very much. Thank you for the invitation. First of all, let me apologize because there won't be any vertex algebra in the talk. And it's not going to be about representation theory either. So, but there's a word vertex. Yeah. Yeah, there's vertex and algebras, true. All right, so I like to start with two conjectures that Kontsevich made several years ago. One of them is a bit imprecise in the sense that it relies on the notion of quantum field theory, and I think there's no commonly accepted definition of a quantum field theory, at least mathematically. But still, let me start with the first one. So, like, given a quantum field theory, whatever that means on, let's say, a flat space, RD, with translation symmetries, let's say, and we have some bundle, let's say F of local fields, then the conjecture states that translation invariant differential forms with values in local fields form an ED algebra, or if you prefer, an algebra over the little disk operad. And so what I want to do right now is to explain you roughly or heuristically what an ED algebra is. So an ED algebra structure on a cochain complex. It consists in the following data. Okay, so first of all, for every configuration of like several disks in the unit disk, let me write it like this. So you have like what? 1, 2, 3, n. Let me give a name to this cochain complex. That's going to be A. We have an operation from n copies of A to A. So to every configuration of disks in the unit disk, we have an operation. Then, okay, so for every path between two configurations, let me write it that way. So we have two configurations. It means that we have two maps like this. And for every single path, we're given a specific homotopy between these two maps. Let me write it like this. So that's a homotopy. All right. There's some associativity constraints. So let me again write a picture. So assume you would be given a configuration like this. And you're given inside, let's say the first one, another configuration. So there's two things you can do. First of all, you can write the map that corresponds to the first configuration here. And then, well, let me put a second tensor that, this second one corresponds to this second thing here. And now you can use the middle configuration inside the big disk to have a second operation. And the associativity constraints tells you that essentially this composed map corresponds to the direct configuration that you will get of 4 guys when you remove this intermediate disk here. Okay? And well, and that's where I'm gonna lie a little bit. Of course, if you have homotopies between paths, you want higher coherencies. And there's a whole bunch of higher homotopy coherencies between all this. And I'm not going to explain how to make sense of this, but there are ways to do that. So let me, instead of give you some feature for these algebraic gadgets. In dimension 1, the theory of E1 algebras is completely equivalent to the theory of A-infinity algebras or strong homotopy associative algebra. In dimension 2, provided that we work in characteristic 0, and that's what we're going to do, E2 algebras boils down to what is called G-infinity algebras, which is strong homotopy Gersten-Haber algebras. So you're going to have a commutative product, a Lie bracket of degree -1, which is compatible with the product, and a bunch of coherencies as well. Okay? All right, so if you want, the higher you go in dimension, the more you can move your disk around, and the more you get something which is commutative up to homotopy somehow. So in dimension 1, you cannot move around, and there's no room to commute things. In dimension 2 already, you can braid things, so that there's some kind of commutativity, and the higher you go in dimension, the higher commutativity is up to homotopy. All right, and there's a last feature, which is whenever if A is an ED algebra, then up to some degree shift, which is by d minus 1, this becomes an L-infinity algebra that is a strong homotopy Lie algebra. Okay, it's related to the fact that the space of configuration of disks in the unit disk, it has the same homotopy type of the space of configuration of points in, let's say, RD. And when you compactify this configuration space, essentially you keep the same homotopy type. And if you look at the top cell of the complex of configuration, actually you recover the opera that encodes L-infinity algebras. All right, so let me make a bunch of remarks about this conjecture. So first of all, the heuristic idea behind this conjecture it's that once you're taking translation invariant differential forms with values in fields, somehow you can move things around kind of freely because you have translation invariance. And the operation you get, you can define them only when disks become small and small and they collide to each other. They are becoming close to each other. And then you perform some kind of operator product expansion. And that will be the definition of the EN algebra structure that Kontsevich has in mind. Okay, so the remarks are the following. So actually, there are ways to make sense of this in some contexts. So there's a lot of works that has been done by Kevin Costello. Also Costello with Guillaume. in the framework of factorization algebras. There's also, previous to this, there was some work of Stefan Hollands, where he relates operator product expansion with some ED algebra structures. Well, all these works, they actually work at least for deformations of free theories. So at least they make sense perturbatively. I think what Kontsevich has in mind, you don't need to have some like a potential with that. I mean, that would be a deformation of a quadratic one. So, like what he has in mind seems to work in the far more general setting. Also, more recently, there was some nice result by Chris Elliott. There's one of these two, and Pavel Safronov, where they also phrase this in terms of factorization algebra. They show that if you have some factorization algebra that has some translation invariance, when you like go to some kind of de Rham complex associated to this, you get something which is locally constant and which is a reminiscence of an E2 algebra structure. All right, and then there's an interesting fact that was noticed by Kontsevich is that and I don't know how precise it is, but he expects that the L infinity algebra structure one gets is related to the Kohn-Kreimer combinatorics for renormalization. The reason being that this L infinity algebra structure, presumably it has to do with deformation theory and with this renormalization, even though like this has been like also in some contexts Costello has some work about it. All right. And maybe one final comment. Yes? Okay, so like he doesn't say anything. So like all what I'm saying here, apart from the recent references, that's explained in a paper that's called Operas and Motifs in Deformation Quantization. And there's like this one-line comment where he says that well, you can model like the operation for infinity algebras as trees, and he just claims that well, there might be a connection with the combinatorics that appear in the in Kohn-Kreimer stuff, even though like it is true that like this L infinity algebra structure in the work of Costello, you can relate it to some perturbative expansion. But in the end, it only boils down to like some kind of homotopy transfer, and there's not much of. I mean, you cannot really see the Feynman graphs in there. So, but at least I don't know how to see the Hopf algebra structure there. Okay, maybe one last point that might speak to you a bit better is that if you have a topological vertex operator algebra, then there's this. Lian-Zuckerman conjecture that tells you that on this, you get a strong homotopy BV algebra structure. And actually, even before that, you know that that's part of the structure. There's a G infinity algebra structure. And the fact that you're having a topological vertex algebra structure, as far as I understand, that's in a situation where the translation operator gets trivialized up to homotopy, and that's exactly the kind of translation invariance that we're referring to here. So that, I mean, like in some way, I mean, that kind of statement might be an instance of this kind of general principle. All right. But this is not what I'm going to talk about today. That was like kind of like general motivation. And Kontsevich has a second conjecture, which is very precise, and which is about it's a kind of discrete version of this, if you want. All right. Yes. So like that should be part of the like so. No. So like yeah. So if you want X would be like your spacetime, and you have like a bundle of fields over it. So if you wanted so the part of the definition would be like you have like an infinite dimensional bundle of fields. Yes. Sorry. Yes. Right. I'm sorry. All right.
Okay. The other question.
No, so like yeah, but basically the underlying graded vector space would be just like a wedge of RD tensor like the fiber at 0. That would be what you have, and on this you would have a differential that encodes I don't know, like essentially you just have this, and on this it is expected to have an EN algebra structure or ED algebra structure. Other questions? All right, so let's move on to the other conjecture, which is about like vertex models. Okay, so I want to be a bit more precise. So just first of all, for simplicity, we're gonna stay in dimension 2. What I'm gonna say is like way more general. It's just that I'll be able to write pictures. So we consider the square lattice Z2 inside R2. Now let me draw it like this. All right. And we're giving ourselves two vector spaces. H stands for horizontal and V for vertical. H could be equal to V. I mean, it doesn't matter so much. And R will be a matrix. It will be an automorphism of H tensor V. So the interpretation of that you should have in mind for this data. So let's assume for a moment it's not needed, but let's assume that H and V are finite dimensional, and that we're given basis of this. So H would be a direct sum, and V as well. So we have EI being a basis of H and Fj being a basis of V. So if you write the matrix R on basis elements, so it will evaluate on EI tensor Fj, and that's going to be Rijkl times Ek tensor Fl. And I'm assuming sum on repeated indices. And we interpret this coefficient here as some weights associated with the following configuration. So like that's a local configuration at a given node of our lattice. And the configuration is that the edge that in comes from like horizontally will be decorated by the basis element EI. Same for the vertical one, Fj, and then Ek, Fl. Right. All right. So now we're gonna play some game. It's the Statesman game. So Which means that we are going to count configurations with their associated weights subjected to some boundary conditions. So more precisely, for every, let's say, yeah, it's not necessarily needed, but let's say convex open subset, let's say a finite size in R2, we associate a space of boundary states. So let me write WU for the space of boundary states. Instead of giving you a formal definition, let me give you an example. So yeah, let me do this here. So assume U would be this, okay? So for every incoming horizontal edge that hits the boundary, we put a copy of the dual of H. And for every outgoing one, we put a copy of H. Okay? And we do the same for the vertical one. Here, we would put like a copy of V star, and here and there. All right. You can easily see that there will be as many incoming and outgoing things. So in the end, in this case, WU is just going to be an endomorphism space of what there's three horizontal lines that are hit and two vertical lines. So that's endomorphism of H to the 3, tensor V to the 2. And that's the space of all possible decorations of the edge, of the boundary edge that you can give by elements of the basis of H and V. All right? Okay, and then we define the partition function that will be a vector in this space. And essentially, it's something like if you decompose it in the basis of this space here. So basis element of this space, that's a given decoration of the boundary edges. And that's just, you're gonna write a huge coefficient where you put the matrix R at all the middle guys that are not determined. So in concrete terms, let's say in this specific case, yeah, let me rewrite it because it's going to be messy otherwise. All right. Okay, so let me give a number to the vector spaces so that it's not too messy. So like this one, these three will be 1, 2, 3, and this is 4 and 5. And now, so what is Z of U in this case? Well, I first apply the matrix R here. So that's going to be R acting on 1, 4. By this, I mean that like R has two legs. it acts on the first copy of H and the first copy of V, which is number 4, and it acts by the identity everywhere else. So like, just be careful. Like, these things are not the indices of this matrix here. Then I can put like R15. Then there's R24, R25, and there's R34. And you can see that there is some choice in the order I've put, but it doesn't matter so much because, like, for instance, like these two, they commute. So like, it doesn't matter if I go from left to right first and then from bottom to top, or in the other way around. Like whenever there's an ambiguity, it actually things could do commute, so it doesn't matter so much in which order I put things. Okay, so essentially that computes. Like if you write in terms of matrix element, what this means, that really computes this the number of configuration associated with the weights and with subjected to the correct boundary conditions. To put what? No. Like definitely, I mean, this matrix acts on like vector space number 1 and 5, and it acts by the identity everywhere else. And this one acts on 2 and 4. Yeah. So you can use the lexicographic order, but then there's some choice. Either you prefer one direction, but whichever direction you choose, I mean, it's it doesn't matter actually. That's for convenience, but it doesn't matter. Somehow, you have to, like the true condition is you have to ask like something about the boundary of your. You want it to intersect like in a clean way, like in a transverse way your lattice. That's the only condition that you have to put actually, and that also like it doesn't like intersect it like infinitely many times, but. No, it's true. Like you're absolutely right. I should drop convexity and ask and put the transversality condition. You're right. Other questions? All right. So we can actually play the same game with inclusions of open subsets. So we would have an open subset U inside another one. And you can easily convince yourself that you can write actually the same thing gives you a map from so W U prime, a linear map from W U prime to W U. Essentially, let me be very quick. I mean, you have your lattice. You have an open subset here and a bigger one there. What you're doing, I mean, the open subset here, so you're picking an element in there. That's going to give you a matrix that gives you that essentially gives you the space, I mean, the state of the boundary states there. And what you do is you fill the intermediate space between these two open subsets by R matrices. So like here, you're saying this to like there's going to be a bunch of R's, and then an A, and then like 4 R's, and you have to put the correct indices to say on which copy of H and V these things act. All right. Okay. And what we can do is to perform the colimits of all this. So let me define WR2 it's going to be the colimit for all this of the WUs, where the transition maps are given by these things. And definitely what you can observe is that the lattice Z square acts on this. So the conjecture says the following. He calls this upside down renormalization. If you're taking chains for the group Z square acting on WR2, so that's the complex that computes like group homology with values in representation. Actually, there is a representation actually in this stuff. This is an E2 algebra. All right. And like there's this similar thing in higher dimension. All right. So I think the idea behind this is that like taking this kind of like you could call this a large scale limit. It's similar to doing something quite opposite, making the mesh of your lattice like smaller and smaller. And somehow when you do this, you have infinitely many like horizontal and vertical line in your open subsets. Then like it's pretty clear what to do like for the, like if you have a configuration of 2 disks in a bigger one, you use this to construct an operation. And then like this thing, it's actually the homotopical version of computing co-invariance. If you take the 0th homology, that's exactly the co-invariance. So like somehow you get a, like your observables are homotopy co-invariance. So that's what allows you to move things around. And that's how you will get like some EN algebra structure. That's the rough idea. So essentially, okay, in the rest of the talk, I want to sketch a strategy for the proof. So if you wish, like the theorem that we prove with Damien Calaque is that this conjecture is true. And I want to sketch the ID for the proof. All right. Sure. Yeah. I completely agree. First of all, there's several things that I don't quite understand about the relation between these two conjectures. First of all, here we're taking translation co-invariance. And on the other side, we're taking translation invariance. And on the other side, it's true that was translation invariant in the strict sense and not homotopically. So like I agree. I mean, there is some analogy between these two conjectures, but it's not complete. I mean, it's not perfect, or I don't understand it completely. So I have to say that like there are several things I don't understand about conjecture A, and also I don't know how to make it like a precise mathematical statement. Like what I like with this second one is like I've essentially understood everything about it. So yeah. Yeah. Yeah, I don't know. So this is a bit difficult because okay, essentially, yeah, you'll see in the proof that like once you have a square lattice, essentially how are we going to replace like a path between configuration? That will be discrete moves along the lattice, like a kind of like step-by-step thing. If you'd like a framed E2 algebra, you would need like rotations or these kind of things. But then, like you clearly see that like with a discrete model like this, you're not gonna be able to rotate by anything else than like pi over 2. So you'll like hardly access to S, like the action of S1, for instance. So to do so, you would need to be able to change the shape of the lattice and to be able to compare things. But that starts to be really way more complicated. I'm not saying it's not doable, but it's way more complicated. Like for all these E2 parts without like frame structure, I don't need to change the shape of the lattice. All right, so the first thing I want to do is to provide a reinterpretation of this thing here. That's a reinterpretation that is pretty much categorical, so you may not like it, but it's super convenient actually. So let me rewrite what we did up to now. So let me write open R2 for the poset of open subset of R2, maybe with some restriction, like some condition on the open subset so that they intersect well the lattice, etc. So it means that objects are the open subset of R2, and there's a morphism and a single one whenever there's an inclusion of an open subset into the other one. What we constructed, this W, together with the map between the different things, it's just a functor from this to vector spaces, but I can land in complexes. I mean, vector spaces is a subcategory of complexes, so that's fine. So like this W, you can reinterpret it as a functor from this category to complexes. All right. And what we're essentially doing is to compute the colimit of this functor. So I want to compute this colimit in 2 steps. So first of all, I want to write another category. Like the T's, like that's a bad name, that's for translation. So I'm taking the same objects and I'm adding, to define this category here, we add a bunch of morphisms. So essentially we add translations, which means that translation will be additional isomorphism by elements of the lattice. So in here, the only morphism we have is there's a morphism from U prime to U if U prime is included in U. And here we add translations by the lattice, which means that typically if you have an open subset here and another one there, there's a morphism from this one to this one, which is first translating the left one into the other one and then include. All right. And actually, so this guy here gets a functor to the category, which I want to call B Z square, which is the classifying category for this group. It's just a category with only one object, and it's endomorphism or just Z2. So essentially, it forgets about the objects and like the morphism that were there and only remembers about the translations. And one can actually check that this diagram here is a pullback diagram. Essentially, this guy is obtained from the bottom one by forgetting all the translations. All right. So now, like, you see that what we have is that actually our W is the pullback of some W tilde through this map, where all this identification here are given by identities. If you remember how I defined this W, it's completely independent about where it is located on the lattice. You can translate it, you get something which is identical. So actually, this functor here comes from a functor that is there. And the claim is that this complex here it's like the correct word, it's the homotopic limit of the functor W tilde. And they're like, so the way you can compute like colimits is by, like there are special types of conextensions. Yeah, so essentially it's a kind of push forward operation. And what we're doing here is we're saying that when we take first the colimit of this W here, the fact that it has a Z2 action comes from the fact that it's a pullback of something that lives there, of which we're taking the push forward along this. And then there's a remaining Z2 action, and then we can like take the colimit for this. So it's a kind of, like if you want integration by part thing, we first integrate along this functor, and then push forward along the point. So that's a like in category theory, that's a like pretty standard thing. But I think the upshot is that this two-step process here can be computed in just one step from this functor W tilde there. All right? No, like, well, it depends. I mean, if you're taking like a colimit, you're gonna get homology, and if you're taking a limit, you're gonna get cohomology. That's just but yeah, I really want to take colimit because there's no choice here. This one has to be constructed as a colimit. This one there would be a choice. But then, like, to make sense of, like, to prove what I just said, you need some statement that some colimit commutes with some limits, and you don't, like, actually, in this case, it is true, but I don't want to get into this. All right, so now we have a functor, and we're taking its homotopic colimit, and we would like to prove that it is equipped with an E2 algebra structure. Okay, so I still have 5 minutes. There's a lot of subtleties there, so let me cheat a little bit. So, all right. So first of all, like one remark. So the Statesman game that we played, it also works with things like this. So instead of having one open subset included in another one, you would have a bunch of pairwise disjoint open subsets included in a bigger one. It doesn't change. I mean, the game is still the same. What it gives us is that we can replace this category by a category that is going to have a monoidal product, where actually I can tensor product open subset by doing the following thing. I take two configurations, I pull them apart in a specific way, and then I take the disjoint union. So there's actually, so there exists like a braided monoidal category. Let me call it that is made that is defined in a way very similar to the T open R2. So with object being configurations of open subsets instead of open subsets. Okay. And there you can define so let me describe heuristically the monoidal product. So there's actually a choice for the monoidal product. So there's 2 points of view of this. So either you define two monoidal products that will be compatible. So there's if you have a configuration, let's say U and another one, so V, we can perform the vertical monoidal product, which is taking the configuration U and the disjoint union with V translated by some vector, with the translation being minimal so that V is above U. Okay? So typically, if, I don't know, you would have like U here and V there, you just move V with a minimal n so that it sits above U, right? And there's a similar horizontal product, which is defined the very same way. With n minimal, so that like V would be on the right of U. And you can prove that, one can prove that these two products are compatible. And it's completely equivalent to have a braided monoidal category or a category which has two compatible monoidal products. If you prefer, you can just take this product, and the braiding is given by the following thing. You just pick like this path. I mean, you use the translation in this category here to show that there's a natural equivalence with the thing where you put the V on the other side and U there. So that's the braiding. All right. So let me end with a statement. Is that now what we can see is that this functor W tilde, it's actually the restriction of this. Of a functor that lives on this category in there. And you can check that it's a braided monoidal functor. So there's a general principle is that like homotopical limits of En monoidal functors, and I should have said that when n equals 2, and E2 monadal category that's the same as a braided monadal category. Is an EN algebra. So we've been, like what we've been doing is announced this functor into a braided monadal functor of which we're taking the colimit. And the colimit automatically becomes an E2 algebra. And that ends the proof. There's actually a catch in this game because one would have to prove that the inclusion of this category in this one is what is called a cofinal functor, so that computing colimits for one or for the pullback is the same. It is not. So there's another step one has to make is to go to a quotient of this category that starts to really look like a discretized version of the little discope, right? So there's an additional step for this to work because, like, just as I said it doesn't quite work. So there's one more thing to do, but I'm running out of time. So thank you very much. Yeah, me neither. Like, okay, I think like the rough idea is that one should think of like this discretized thing as really a kind of discrete version of a quantum field theory. But there's a discrepancy. Like that was your question. First of all, in this case, we're taking homotopy coinvariance, and there's like two problems. Like in the first conjecture, we're not taking anything homotopy. So like why in the first conjecture we wouldn't do this and we would do it in the second one? And also in here, we're taking coinvariance as opposed to invariance. For this second thing, it's not a so big problem because like in this very specific case, we can also prove the same conjecture for invariance instead of coinvariance. It seems less natural because the proof requires more technicality because you need to prove that this colimit commutes with some limits there, but it works. But still, I think coinvariance makes much more sense in this case, while invariant do make more sense in the other case. I don't know, that might be like a stupid duality thing that here I'm considering like rather like the kind of thing that I'm considering is states, while in the other case that was field. So it might just be something about duality, at least for the coinvariant versus invariant thing. For the homotopy versus like strict, I don't know. Mm-hmm. Sorry, that's what?
What I'm saying is that
Probably yes, you're right. Yeah, it might just be this, right? Yeah, so I have no idea, but like typically if like the horizontal and vertical vector space would be the same, and you would take like some R matrix that satisfy the Yang-Baxter equation. I don't know what this says on this E2 algebra here, but it is a very good question, but I have no idea. Also, I would guess, but this is like somehow purely topological in the sense like things that give, I mean, like anything that comes out from an EN algebra that gives only the topological part of like any kind of theory you may have. Like I don't know how to recover, like, yeah, actually that would be interesting to recover vertex algebras from this kind of picture. I guess you would need, or like that the R matrix gets some spectral parameter to be able to do this. I don't know. Yes. So actually, yeah, it depends what you mean by the algebra is trivial. It's quite. I mean, it's so the algebra would become like this. It's not quite trivial. I mean, so this first colimit, it's going to be just a huge endomorphism algebra of like infinitely many copies of these, like organized in some way. And still, taking the colimit, I mean, taking this co-invariance, yeah, probably it might kill everything. Yeah, you're right. Yeah, I don't know. Actually, like even computing this gadget is not easy. So I don't know. And to be honest, I don't know what it says. Like having this E2 algebra structure, what it says on the on concrete situations. If it gives more information that we didn't have before. Mm-hmm. 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 Yeah, I don't know. You need to. I think to get something interesting, you need to change the maps that you allow. Because if you just change the like kind of domain that you allow, it doesn't change much. Actually, so the yeah. Yeah, I don't think it. Yeah, I don't know. I'm not sure. Okay, I haven't thought about this, but definitely if you only change the shape, actually, you can restrict to like disk or squares or like rectangles. The embedding, like there's a bunch of subcategories of this where you restrict your class of open subset that are allowed, and all these embeddings are final. So that's computing the colimit on here or like restricted to the subcategory. It doesn't change. So like I suspect that it's unless you add new morphism, but if you just like put a restriction on objects, I'm pretty skeptical that it will work. And morphisms? Okay, yeah, maybe it's a good suggestion. Yeah, probably true. So the point is that like the result would work for in general for like when you start from here and you get like a functor like this that would extend to a braided monadal functor. So you don't need that it comes from the construction I gave. Actually, I have a few example like even in general dimension of of some kind of discrete model that that recover this higher Weyl algebra. I don't know, I mean, if you know this. Like in dimension 1, there's this thing by, like Kosel and Guillaume could recover the Weyl algebra by using like a simple quantum field theory in dimension 1 that they call topological quantum mechanics. And actually, you can perform a completely discrete version of this that also gives back the Weyl algebra. The discrete version has like the nice feature that it's like at all steps it's purely finite dimensional, while the quantum field theory thing you have to take like compactly supported forms on R with like values in something, and then you take like that's your fields, and then you take functions on this. So you're taking symmetric algebra on some infinite dimensional space. There's a lot of infinite dimensional complication in this case that you can just completely avoid by using this kind of gadget.